We just had a lesson on the steps for drawing Lewis dot structures, so I thought now we would apply them and actually practice drawing our own Lewis dot structures. So you have this Lewis dot structures and Vesper practice packet. There's a lot of practice problems on here. There is like over 20 Lewis dot structures for us to practice together, but all of this practice is excellent, excellent, excellent. We are going to be doing different sections of this packet as we learn new material. We are just going to be focusing on the Lewis dot structure column today. Eventually, when we learn about the Vesper shapes, we'll be able to fill in the number of bond regions and the number of lone pairs in order to write what molecular shape. And then eventually, we will still be able to figure out what the molecular polarity of the molecule is. But today, we're just doing our Lewis dot structures. So you will need out today are the back of the notes page where it has these steps, because I'm going to be referring to what we are actually doing. And then you'll also need, oh my gosh, of course we need our periodic table, because we know these valence electrons are actually super important, because that's the first step. We need to count how many valence electrons each atom in the molecule has in order to figure out what's the number of total valence electrons within the molecule that could potentially be shared and form bonds. Okay, so let me get out a pencil here. All right, so we're going to first start by drawing water. And you're like, I know what the structure is. I've seen a Lewis dot structure for water all the time. I could draw that right now. That's great for you, but we're going to actually see if we can apply our steps and it'll turn out the way we expect it to. So our first step is to count the total number of valence electrons available. So what that means is I look at all of the different elements in my compound and I find them on the periodic table and say, well, how many valence electrons do you got? Okay, I add up everybody. So look in here, it looks like I have 2 hydrogens. So since I have more than 1 hydrogen, I'm going to write 2. How many valence electrons does hydrogen have in group 1? He's got 1. So 2 times 1 would be the total amount of valence electrons that hydrogen is bringing to this molecular table. Then I got oxygen. I only have 1 oxygen. And my he's fine. And my cute little 1 oxygen, he's got 6 valence electrons. So I'm going to go plus 6. So my total number of valence electrons for this structure is, I broke my pencil, is going to be 8 total electrons. Cool. All right. So the next step is to place the central atom in the center and then the remaining atoms on the outside around the central atom. So tips for picking your central atom, it is usually the atom that you have the least of, okay? And a lot of times it's the atom that is written first in the formula. It is never hydrogen, because we know hydrogen can only make 1 bond. So since the first atom in my formula is hydrogen, I'm going to skip over him real quick and get to oxygen. He's my only other option for my central atom if I want all 3 of these things to be connected together. Hydrogen cannot connect to anybody but just one other person. So I got my oxygen in the middle, and then I'm going to put my hydrogens just, on the outside somewhere. Notice I've not done any lines. I've not done any dots. I've put letters of the alphabet on my page. Okay, so that is step 2. Step 3 says you're going to use a pair of electrons to bond each of the outer atoms to the central atom. Okay, so that means I'm going to be drawing a line. A line represents that shared pair of electrons. Each time I draw a line, I'm going to be taking 2 off of my electron counter. So I'm going to draw a hydrogen, connect him up to oxygen. That means now I have 6 electrons left over. And then I'm going to connect the other hydrogen up to oxygen. So that was 2 more electrons taken away. I now only have 4. All right. The next step number 4, says to distribute remaining electrons to first my outer atoms. And then after I've got them covered, I'm going to distribute them to my central atom to make sure everybody is happy and has their full stable valence shell. My outer atoms are hydrogen. So before you start putting some more dots around my hydrogen, trying to make them get 8, we know hydrogen can only have 2 in that first shell, which is his valence shell. So since each hydrogen has a bond line connected to him, each one totally feels like he has a satisfied 2 valence shell. So we done on the outer guys. Now we zone in on that central guy. We're looking at oxygen. He has 1, 2 from this bond line, 3, 4. He only has 4 valence electrons, and he will need 8. But luckily, you guys, I have the 4 leftover valence electrons from my electron counter that I can give to oxygen and make him feel happy. But when we are putting extra electrons on an atom, we put them in pairs, okay? So I'm going to put a pair of dots. So that's 2 electrons. So I have 2 left. And then I'm going to put another pair of dots. So that's 2 electrons, and I am now 0. Okay, so that is my Lewis dot structure for water, you guys. You have seen this before. You're like, great, that's what I expected to get. But why does he not look weird? And what I mean by weird is, why does he not look like y'all probably seen this before a lot, right? Technically, this is a correct Lewis dot structure, because when we start learning about this 3D molecular shape that water likes to take, depending on the way I'm looking at water, that would absolutely be correct. Regardless, if I have drawn the correct number of bonds and I have drawn the correct number of pairs of electrons on every single atom within this molecule, there is no reason for me to take off any points on this, okay? Both of these would be correct structures. It is whichever way you would just like to do it. And you'll get better at feeling comfortable on the way you want to assemble your Lewis dot structure as you do more and more practice, because you'll be able to do things like kind of anticipate what the kind of two-dimensional shape would look like, or at least in a way that would be most pleasing to you. That was a lot of talking. Let's move on to the next one. Okay, so the next one is, oh, y'all, I would just call this chlorine, because this is one of my diatomic elements. This is one of my Hofbring coals, right? So if I ask for a sample of pure chlorine, he will always come in twos. Let's see what this molecule of chlorine looks like. Okay, I'm really excited. So we got chlorine. Let's see how many valence electrons he has. I got 7 for each one of those chlorines, and there are 2 of them. So 2 times 7, he has totally 14 electrons. Okay, we are ready here. We are ready here. Next step is to place the central atom in the center and the remaining atoms on the outside. There are only 2 atoms here. Yeah, so some of these will only have 2 atoms involved. That is okay, just put both of them on the table. They will have no choice but to be somewhat near each other and will be available for you to connect them, hopefully, in some way or another. So we'll put chlorine and then chlorine. Sounds good to me. Okay, no central atom, but they are there. We got that. Okay, it says now to use 1 pair of electrons to bond each outer atom to the central atom. Once again, we don't have a central atom, but how about let's use a pair of electrons to bond these chlorines together so they are not flying away from each other, because according to my diatomic rules, you've got to be connected in twos. So here we go. Every time I draw a line, that's 2 electrons. So that was 1, 2, so we're down to 12. So everybody's connected up. We're feeling good. Now I'm going to put the leftover electrons around the outer atoms first. And then if I had a central atom, I would put it on the central atom. So hopefully these outer atoms, after I take care of them, will get my ticker down to 0. So it looks like each chlorine, if I focus on this one right here, he's got 2 so far. He needs 6 more. So I'm going to put the 6 electrons in lone pairs on the other sides of my chlorine atom. So 1, 2 on the top, 3, 4 on the side, 5, 6 on the bottom. So now he's got 1, 2, 3, 4, 5, 6, and 7, 8 in that bond. So I've used up 6 electrons making that happen. I have 6 left to go, which you're already anticipating being like, okay, this is sounding pretty good, because that chlorine over here also needs 6 to satisfy his octet. So I've done 1, 2, 3, 4, 5, 6 dots, and then that's 7, 8 for the pair of electrons. I am now done. That is my structure for the chlorine molecule. Just 2 chlorines, diatomic chlorines connected together. I can also see that this chlorine is connected by a single bond. That may not be the case for some of your other diatomics, like O2 or N2. We'll have to see. I bet I've given you some examples of other diatomics who have different numbers of bonds connecting them somewhere in this packet. That will be exciting for us to find out together. Okay, next one. I've got CH for carbon tetrahydride. So I'm looking for carbon. Carbon is great. He has 4 valence electrons, and there's only 1 of him. And then hydrogen, we've talked about before. Hydrogen has 1 valence electron, and we have 4 hydrogens, each with 1 valence electron. So the total number of electrons here to distribute throughout this molecule is 8. Okay, central atom in the center. I have, luckily, more than 2 atoms here, so somebody's going to go in the center. It is never hydrogen. Also, there is the element that is usually the least abundant, so that's going to be my carbon. So we put carbon in the middle. I'm like, okay, put 4 hydrogens around carbon, not connecting them up to anything yet. Cool. Now I'm going to connect all hydrogens to the central atom using a pair for each line, or 2 for each line. So I would go 1, 2, 3, 4, 5, 6, 7, 8. So I've used 8 electrons. Oh, I've already used my 8 electrons just connecting everybody up to the central atom. And you were like, I've got a lot more rules left to do. What's going to happen? Well, the next rule is to distribute any remaining electrons, which I have none, to my outer atoms. Well, my outer atoms are all hydrogen, and hydrogen is like, I'm fine, we're good. Okay, well then, after I do it to the outer atoms, what about that central atom? Carbon is also fine, because each bond is 2 electrons, so he's got 1, 2, 3, 4, 5, 6, 7, 8. So sometimes it looks like, oh no, I'm gonna run out, but go ahead and make sure you check, and make sure you do check everybody, to make sure we don't have to do something sneaky like make a double or a triple bond. Okay, let's see this next one, NH3. So we could call that nitrogen trihydride, or a more common name for him would be ammonia. So let's count how many valence electrons total within this molecule. Nitrogen is in group 15, right? So he's got 5. We only have 1 of him. And then I have 3 hydrogens, each one with 1 valence electron. Okay, so I have a total of 8 electrons. We are ready. My central atom, it can't be hydrogen, so it was definitely going to be nitrogen. Yes, and then I put my 3 hydrogens on the outside. And if you're noticing I didn't put them evenly spaced, it does not matter to me at all. I have a prediction, since I've done this several years, of what this structure is going to look like. But I think a good rule of thumb, is to kind of think about like this being a box around that central atom. And I tend to start off by putting any of my outer elements just kind of on the 4 sides of that box. That is what I find most helpful for me, especially visually. It helps me, like, you know, make my structure look nicer. It does not matter though, as long as I see the correct number of bond lines connecting the same correct number of atoms and the correct number of dots around things. Huge tangent, but let's go. So I got to connect everybody up to the central atom using 2 electrons each time. 1, 2, 3, 4, 5, 6. I've used 6 up. That means I'm down to 2. Okay. Now distribute remaining electrons around the outer atoms. They're all hydrogens. They're good. Okay, well now I got to look at that central atom. Central atom has 1, 2, 3, 4, 5, 6. Nitrogen has 6. He needs 2 more. Luckily, I have 2 to give him, and I'm going to give it to him in a lone pair on that central atom, which means I've completed it. Everybody is happy. We are feeling good. Okay, I actually think I want to come back to number 5. Well, no, let's do number 5 now, because there's a lot of fun things coming in with number 5. So number 5, I know a lot of you guys are like, oh, SO3, that is sulfite. He's a polyatomic ion. And I'm like, no, he is not. If he was one of my polyatomic ions, it would be SO3, but he would overall have a -2 charge. This is just plain old uncharged molecule of sulfur trioxide. So let's see what sulfur trioxide is bringing to the table. So I have sulfur. He and oxygen are actually in the same group with 6 valence electrons. So my 1 sulfur has 6 valence electrons, and my 3 oxygens each have 6 valence electrons. So the total number of valence electrons in this molecule is 24 that I will need to distribute to everybody. Okay, I'm going to actually write my structure kind of up here at the top. It is fine if you decide to take up the whole page, but usually when I give you a big old box here, that may mean something is coming that will require you to draw more than one structure. And if you're thinking resonant structures, maybe. We'll see. It's going to be a nice little surprise for us. So we have sulfur's going to go in the middle because I have only 1 of him. And then we will do my oxygens on the outside. Yep. Connect everybody up to the central atom using a pair. 1, 2, 3, 4, 5, 6, right? So I've used up 6 electrons, and that means I'm at 18. Fill up the outer atoms first. Each oxygen only has 2, so each oxygen needs 6 more. So I'll put them in pairs, 1, 2, 3, 4, 5, 6, on the remaining other sides of that oxygen atom. So I've used up 6 here. I have to close my eyes because I'm trying to do the mental math. I've used 6 here. I'm now down to 12. Also, you are allowed a calculator in my class always. So if you need to subtract simple numbers like this, there's no shame in that. You're far less likely to make mistakes, so that's an option that will always be available for you. Okay, I got 2 more oxygens. This one also needs 6, so I'm going to go 1, 2, 3, 4, 5, 6. Okay, subtracting 6 from 12. I now have 6 left over. You're like, this is looking great. I'm so excited. So 1, 2, 3, 4, 5, 6. You're like, cool, we are good, bye. And you want to walk away and like pat yourself on the back, but no. We got to check everybody out when we're done. Specifically, we have not even looked at that central atom. He needs to be happy too. uh-oh. He has got 3 bonds, which means he only has 6 valence electrons. 6 valence electrons. I run out of electrons, which means we get to go to this giant section in our notes if there are not enough electrons. I get to make multiple bonds, double bonds, triple bonds, whatever. So it says if I'm 2 electrons short, I get to take a pair of electrons from the least electronegative outer atom, and then I'm going to use it to form another bond between it and that central atom. You're like, cool. All right. Who is my least electronegative outer atom? They all the same? Well, if these were different outer atoms, I would pick the one that is, if this is where electronegativity increases, I would pick the one that is furthest from this top corner. And even more accurately, I would probably use my chart of electronegativity values to see which one is the least electronegative out of my choices. Anyway, they're all the same. If they are all the same, it does not matter. Like, how am I supposed to know whether I pick from that oxygen or that oxygen or that oxygen? So if you have yourself asking this question, being like, what do I do? Doesn't matter. You've got a resonance structure, which means this molecule actually will resonate in between all of the possible bond types. Okay, so for the purposes of creating this double bond, let's pick one of these oxygens and commit to it. Let's pick this side oxygen. So it says what I'm supposed to do is I'm supposed to take a pair of electrons from that guy and use it to share with that central atom. So that means I literally get to erase, which you will be doing things in pencil always in my class, and I have to take a pair away. I don't know. Doesn't matter. Now that pair, I'm deciding, okay, he's sharing now with this sulfur. Cool. Now is everybody happy? Let's check sulfur again. 1, 2, 3, 4, 5, 6, 7, 8. He's got 8. Yay. You're like, but the oxygen, he's still fine too, you guys. 1, 2, 3, 4 that are in bonds with that sulfur. 5, 6, 7, 8. So sharing is caring with covalent bonds. Now everybody's octet is satisfied, but I've got to represent these 3 different resonance structures, which means I'm going to draw the other 2 possible types somewhere down here, and then we're going to draw double-headed arrows kind of connecting everybody up together. So I've got, let's draw down here. I got sulfur. So I have my oxygen there. That 0 is going to totally look like an oxygen pretty close by, so I'm going to erase that 0 from my electron counter and put him up there. Then I'll put my other oxygen here. And this time, this resonance structure, I'm going to show it with the double bond going to this oxygen. So on the previous example, it was over here. Now I'm going to show him going over here. But keep in mind, in order to make that double bond, I ain't got 3 pairs anymore. One of those pairs went into that double bond, so he's only going to have 2 left. Okay? And if I really wanted to be technical, we know all of these electrons in the bonds or on the lone pairs are negative, so they're going to want to spread out from each other. So if you want to be, exact, you can kind of put them catty corner on the corners of this oxygen molecule. You do not need to do that. This would totally be acceptable for me, but the main thing I'm looking for is I need to see them in pairs. Do not put them spread all out 4 apart. Also, do not put them in between the oxygen atom and the lone pairs. I've seen and the bonds. I've seen some dots in between my atoms in a bond, and that is not a choice for you. So anyway, that was another big tangent. I'm on lots of tangents today, and that is fine. Okay, my third option of a resonance structure is going to be going to that top oxygen atom. So I'm going to draw that. So that top oxygen atom would now only have 2 pairs of electrons. And then the other options of oxygens would have their 3. And if you're just getting comfortable with showing the different resonance structures, it's a good idea to go on each one of your structures and check and be like, okay, are all my atoms and all of these different types of things that I've drawn, are they all satisfying their octet? Because sometimes we get a little jumbly when we are swapping that double bond around. So my molecule will actually resonate between these 3 types of resonance structures, which is really fun. So congratulations, you've just done some resonance, which we love. Okay, let's go to the next example I want to do. Let's just kind of keep chewing through in order. Let's see. Okay, number 6 on the back, I've got carbon tetrachloride. Let's see how many valence electrons he is bringing. We've got carbon again. Each carbon has 4 valence electrons, and we only have 1 carbon. And then chlorine, there are 4 of them. Chlorine is a halogen in group 17, so he's going to have 7 valence electrons. So 4 times 7, this is where you may need your calculator. 4 times 7 plus 4 is going to give you 32. So my central atom is going to be carbon, because there is one of him. And then I've got 4 chlorines that I will put around my carbon. Haven't drawn any lines yet. Connect everybody up to the central atom. 1, 2, 3, 4, 5, 6, 7, 8. I've used 8. So 32 minus 8 is going to give me 24 electrons. Like that. Still a lot of electrons. Well, I got to fill up those outer atoms. And you guys, the outer atoms are not hydrogens. In fact, none of them are hydrogens. They are all chlorines who all will need 8. Each one only has 2. So each chlorine atom will need 6 more. So I'll put them in pairs. 3 pairs of electrons on each chlorine. So that is 6 removed from my 24, which means I'm down to an 18. This chlorine gets 6 to complete his octet, which means he's down to a 12. This chlorine gets 6 to complete his octet, which means we are down to a 6. You're like, this is looking good to me. And then filling up the last chlorine, we are now at 0. Check that central atom though, because on the previous example, we needed sulfur to change in some way to get him to be satisfied by making a multiple bond. Carbon, he's good with 1, 2, 3, 4, 5, 6, 7, 8. 4 bonds to carbon. That's his octet. Amazing. Okay, next one. Y'all are like, carbon dioxide, I've seen this 1,000 times. Well, let's see if we can draw this based on our rules. We've got a carbon. That one carbon has 4 valence electrons. We've got 2 oxygens. Each oxygen has 6. The total number of valence electrons able to be shared within this molecule are 16. Okay. Central atom in the center, that's going to be carbon. My outer atoms are both of the oxygens. I'm just drawing them on opposite sides. Connect everybody up to the central atom. 1, 2, 3, 4. I am now down to 12 valence electrons. Fill out the outer atoms. 1, 2, 3, 4, 5, 6. I've used up 6 to fill up that oxygen because now he is happy with his 8. And then 1, 2, 3, 4, 5, 6. I'm out of valence electrons. The outer atoms are happy, but let's check out this poor carbon in the middle. He only has 1, 2, 3, 4. Oh, goodness. Let's get back out my rules again. Oh, I am 4 electrons short. Oh, she's even giving me 2 choices here. If I've got 4 electrons short, it's fine. It says if one outer atom is less electronegative than the others. Well, they the same. So neither one of these oxygens is less electronegative than the other. They are equally electronegative. So maybe we go to the second rule. It says if 2 outer atoms are equally least electronegative. Yes, that's what we have here. I get to take a pair of electrons from each atom to form 2 more bonds between that atom and the central atom. So I will be creating 2 double bonds here. Okay, sounds good. So when we made double bonds on our last example with the sulfur trioxide, all we had to do was erase a pair of electrons on that outer atom and say, boom, you're now in a shared pair as a double bond. And I got to do that for my other guy because this carbon is not 2 electrons short. He's 4. He needs 2 extra bonds. Okay. So now what I have here is I have 2 double bonds coming from the carbon to each one of his oxygens on the outside. I can check and count and see, okay, carbon has 1, 2, 3, 4, 5, 6, 7, 8. He's happy. Each one of my oxygens has in the lines or in the bonds 1, 2, 3, 4, and in the dots 5, 6, 7, 8. Good. That's carbon dioxide. I'm going to do a few more for you. If we were doing this in class together, I would not be doing nearly as many of these examples, but I'm figuring if you were watching this video, you probably will want a lot of examples of me working with you guys. So I do want to actually do HBr because I think it's a wonderful, wonderful, wonderful example. Okay, so hydrogen is up first. He has 1 valence electron. Bromine is also in group 17, just like my chlorine was that I've used before. And I have 1 of him. And he's got 7 valence electrons. So my total here is only 8. Not a big deal. Central atom. I only have two atoms. So just put them next to each other. Okay. And I know it says connect everybody up to the central atom, but there's not a central atom. We'll just connect them up together so everybody is connected to make a molecule. Or else if we're not connecting them, we have no molecule. We just have individual atoms, which does not work for us. So we've got a line 1, 2, making that line. So now I'm down to 6. Now I'm going to see if both of these guys are satisfied. And if not, I'm going to put those electrons around them to satisfy their octet. Hydrogen, he is good. He only needs 2 from that bond. Bromine, nope, he needs 8. Right now he only has 2. Well, that's okay. 3, 4, 5, 6, 7, 8. So I added 6 electrons in pairs around that bromine to get rid of that. Okay. So this was just another example that I wanted to work through with you guys to show you what happens if you only have 2 atoms. Sometimes it kind of trips you up because you're so used to central atom, outer atoms. But if I just have 2 atoms together, they just go stick together and I go make sure they're all good at the end. Okay. Now let's do arsenic tribromide. This one's a good one. So arsenic, he's super fun. He is in group 15, 5 valence electrons. I only have 1 of him. And then 3 bromines. We used bromine in the previous problem. Each one of those guys has 7. So that math is going to give me 26 electrons to be used in this molecule. Arsenic is going to go in the middle. Ooh, I keep breaking my pencil today. That's how you know I'm excited about drawing Lewis dot structures. And then I've got my bromines on my outsides. Okay. Connect everybody up to the arsenic. 1, 2, 3, 4, 5, 6. So I'm now down to 20. See, I'm going a little bit faster, and hopefully you guys are like picking this up. Outer atoms filled up with electrons. Each bromine needs 6 more to be happy. 1, 2, 3, 4, 5, 6. So now I'm at 14. Check out the next bromine. 1, 2, 3, 4, 5, 6. Now I am at, what is this? Math, 8, hopefully. Yes. Then I got 1, 2, 3, 4, 5, 6. Now I'm left over with 2. Each one of my bromines are happy. They have 8. Let's check out this arsenic. He only has 3 bonds. So in those 3 bonds, I've got 1, 2, 3, 4, 5, 6. Well, he probably wants those last 2, and I will put that as a lone pair. Cool. Let's see. I maybe want to do 2 more. And then if you are an on-level student, that will be the only 2 more I do for you, because I do want y'all to practice this doing on your own and not just sitting here and watching me and following me and be like, yep, I can do that. Yep, I can do that. We're going to use your brain a little bit. But honors kids, I'll kind of talk about the very, very last page that y'all have, because there's some fun stuff on there for y'all. Okay, so we would call this hydrocyanic acid, which is super fun. I got 3 different things here. This is why I wanted to do this one. So we've got hydrogen. Hydrogen has 1 valence electron. I've got a carbon who has 4 valence electrons. And I have a nitrogen who has 5 valence electrons. Looking good. Okay, so we have a total number of 10 electrons to use in this structure. Now this is a little trickier because I have 1 of each type, so I got to use some of my guidelines on picking which one is most likely going to be the central atom. I've got some suggestions like it's the least abundant. It is not helpful to me. It is listed first in the formula. Well, first in the formula is hydrogen, and we know hydrogen is never the central atom. So I actually need to maybe look at my electronegativities. My least electronegative atom is going to go in the center. So if I'm looking here, I've got hydrogen, carbon, and nitrogen. Hydrogen, carbon, and nitrogen. Well, sometimes when you're comparing the electronegativity with hydrogen, let's get out our electronegativity values. I think that may make me feel a little bit better. So whoever is the least electronegative, I've got carbon in this case. Well, first of all, whoever's the least electronegative is going to be carbon, between carbon and nitrogen. And I have kids every year being like, but hydrogen, he's got less electronegativity than my carbon. And you know what, you guys? Yes, he does. But is hydrogen ever going to be in the middle? No. So I've got to put carbon in the middle. That was a big tangent. That's okay. We had to look at electronegativity, so it is useful for us to kind of go over that again. So I have hydrogen and nitrogen on the outsides of my carbon. Connect everybody up to the central atom. 1, 2, 3, 4. I'm now down to 6. Now I'm going to fill up the outer atoms with electrons. We good over here with hydrogen. Nitrogen, oh, he needs 6 more. 1, 2, 3, 4, 5, 6. Amazing. We're out. Everybody on the outside is happy, but carbon, oh no. He needs 4 more electrons. So we're on the 4 more electrons short rule. If I need 4 more electrons, if one outer atom is less electronegative, that's what we're dealing with here, right? We've got totally two different outer atoms, which means one of them is going to be a little bit different in electronegativity, which means I am not making two double bonds like we did up here. Last time our carbon was 4 electrons short. I'm going to pick the least electronegative atom. And guys, it's actually hydrogen, but can hydrogen share? He got no lone pairs. So carbon has to steal 2 more bonds from the only element that he's connected to that actually has lone pairs to steal from. So I get to erase 2 pairs off of that nitrogen and say those 2 pairs that you did have are now going to turn into bonds shared between nitrogen and carbon. So the result of that is carbon is totally happy. Each one of these lines is 2. So I got 1, 2, 3, 4, 5, 6, 7, 8. And nitrogen is still happy if there's still 2 electrons in each line. 1, 2, 3, 4, 5, 6, and then 7, 8. Noticing how just structurally what makes me feel good is that the remaining lone pair that I did not erase is the one farthest from the other negative electron, that bonding region situation. Okay, I think I want to do... Yes, I want to do number 14. So we're going to flip the page. And number 14 is all the way down here. We have a charged ion. This is, in fact, a polyatomic ion. This would be nitrite. So let's see how I can draw a Lewis dot structure for my nitrite. So my first thing is I got to count up the available valence electrons. Nitrogen in group 5, he's got, or 15, he's got 5. Then I've got 2 oxygens, and each one of those oxygens has 6. What is going on here? That means add 1 electron. I have a negative charge, which means an electron was gained. So to this original value of 1 nitrogen and 2 oxygens, they've got an extra negative charge. So that means total in this nitrate, I got 18 electrons. Okay. So let's see. My central atom is going to be nitrogen. And my outer atoms are going to be oxygen. Connect everybody up to the central atom. 1, 2, 3, 4. I've used up 4, so I have 14 left. I almost got confused. Then satisfy all the outer atoms. So each oxygen needs 6. 1, 2, 3, 4, 5, 6. So that brings that counter down to 8. And then I've got 1, 2, 3, 4, 5, 6. So that goes down to 2. Okay, so the outer atoms are filled up. Put any remaining on that central atom in a pair. 1, 2, we are out. But even with me putting that pair on nitrogen, he's still going to be 2 electrons short. I've got to make a double bond from one of my outside guys. They are both oxygens, which means it does not matter which one I steal from to make that double bond. Which means there are 2 possibilities, 2 resonance structures. One with the double bond coming from this oxygen, one with the double bond coming from that oxygen. So we must draw both types. So let's pick one oxygen to start off with. Let's pick this oxygen over here. Say, no, ma'am, that lone pair is not for you anymore. It is shared. Okay, so that's one resonance structure. But there was a rule that said, if you are dealing with a polyatomic ion, you must put brackets around your structure and show the charge on the upper right side of your brackets. So that means I got to bracket this up and put that -1 charge on the outside, okay? I got to draw another resonance structure. So my other resonance structure, I'm going to drop it down right here showing the double bond over there, which means if the double bond is connected to that oxygen will now only have 2 pairs of electrons. Right? And then this other guy now is connected with 1 bond, which means he will have 3 pairs of electrons to himself. Still a polyatomic ion, so still needs brackets. Also needs a -1 charge. Okay? It is a resonance structure situation, so we will show my double-headed arrow showing that that molecule also... Ooh, I forgot my lone pairs on my nitrogen. Oh my goodness, there we go. So that molecule will actually resonate between one structure and the other, which is really cool. Okay, so on level, kiddos, this should hopefully get you guys started. There's so much amazing good practice in here. So I know our rules that we did in our notes, y'all, there's a lot. You do not have to memorize these because pretty much you'll get very quickly good about knowing what you have to do. Even if you get into weird situations where you've run out of electrons and need to make multiple bonds, it will start to become more and more natural to you. Just follow your steps, count up number of available electrons, put the central atom in the center, put everybody else on the outside, connect everyone to that central atom, fill up the outer atoms, check out that central atom. Make sure everyone is happy. Make sure you also show all resonance structures, and make sure you do not have to make more than one bond. And if you do, you figure out which one of the outer atoms to take it from. Okay, honors kids, stay with me. We are going to flip to the very, very back page that I have given you, which is a super fun page. Now the very, very, very back page, let's see. These you do not know. So we're actually going to write for fun. You were like, fun? Why would I even do this? Because it's fun. It's fun, you guys. Okay, so for fun. In other words, you don't need to know this. This. Okay. I thought we would do some of these because these are some of my really funny, you probably see it coming when you see like a 6 fluorines or 5 chlorines. These are some of my expanded octets, so I thought that this would actually be pretty fun. I would like to do, I actually want to do 24 and 25 because these are kind of fun. Okay, so 24, I've got phosphorus, and phosphorus has 5 valence electrons. So my one phosphorus has 5 valence electrons. And then my chlorines, who I have 5 of them, each one has 7 valence electrons. So my total number of electrons here is going to be 40. It's a lot of electrons. Okay, let's see what we can do. It's going to be phosphorus, who's your central atom. Now I got 5 things around, so it's not really going to be as clean as putting one atom on each of one of my 4 sides. They're just kind of be, you know, all over, spread out around that phosphorus. Okay, still the rules still apply. You guys connect everybody up to that central atom using a pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That brings me to 30. Take care of the outer atoms. Each one of those chlorines is gonna need 6 more. 1, 2, 3, 4, 5, 6. Now I'm down to 24. 1, 2, 3, 4, 5, 6. Now I'm down to 18. 1, 2, 3, 4, 5, 6. Now I'm down to 12. 1, 2, 3, 4, 5, 6. Now I'm down to 6. And you're like, I think I know where this is going. Yep, 1, 2, 3, 4, 5, 6. Yep. Check that central atom. Make sure he has 8. Oh, he does not have 8. He's got 10. And you're like, what do I do now? That is okay. According to our rules, it's like, you guys, if you've got too many electrons, we don't even have to place any extra electrons, okay? I just have an expanded octet in this situation. So you're going to roll with this. There's no other way for 5 chlorines to be connected up to a phosphorus unless he does have an expanded octet. You do not need to know this, but I did want to do it because I don't think it's that much of an extension in our methodology here. It's just you got lots more things connected to the central atom. This question number 25 is one of my favorites. First of all, it's got a noble gas in here, which you're like, what is going on? Sometimes my noble gases, very rarely, sometimes they can react, and a lot of times they react in a way to make these really weird expanded octet molecular structures. So let's see what I'm going to make with xenon tetrafluoride. Xenon is a noble gas. This is going to be the first time we write an 8 coming from any one of my atoms. He's bringing 8 electrons. And then fluorine, I have 4 of him, each one with 7 valence electrons. So I got 36 total electrons. Xenon gonna go in the middle. And I got my fluorines, all 4 of them on the outside. Connect everybody up to the central xenon. 1, 2, 3, 4, 5, 6, 7, 8. That brings me now down to 28. Each one of my fluorines needs 6 more. 1, 2, 3, 4, 5, 6. So 22. 1, 2, 3, 4, 5, 6. 16, right? Yes. 1, 2, 3, 4, 5, 6. That is 10. And then 1, 2, 3, 4, 5, 6. So then I'm at 4 left over. And y'all are like, wait, Xenon is totally has 8. He's super happy. Well, I got to put these 4 electrons somewhere. It totally says just place the extra electrons on the central atom. You're like, what? Place them in pairs, though. Not a big deal. This is just one of my weird expanded octets, you guys. He's got 1, 2, 3, 4, 5, 6, 7, 8 electrons from my bonds, but also 9, 10, 11, 12. That's an expanded octet. Okay. Nice. This one says a bonus. I feel like this whole entire back page is a bonus, but I love this one because it actually shows how these polyatomic ions work together in an ionic compound. It says draw the electron dot structure for the following. Sodium. Well, this shows sodium, who has lost his 1 electron. We know sodium, group 1 electron. Okay. So his dot structure would just be this. No more valence electron. He's gotten rid of it. Brackets the positive charge on the outside to tell me that that's what has happened to make sodium look like that. And then phosphate. Or phosphite. And y'all are like, yo, PO3. I just get to draw a Lewis dot structure in this place for him. We love that. Okay, so phosphorus has 5 valence electrons. I'm going to write my valence electrons down here. And I have 3 oxygens, each one with 6. And this -3 tells me to add 3 electrons. So down here, I'm going to say +3. Let's see if Miss Sabaka can do the math in her head. 3 times 6 is 18. +3 is 21. +5 is 26. Hopefully I did not embarrass myself and count up the wrong number. I will realize my mistake if that is happening to be true. Okay. Phosphorus is going to go in the center, right? My 3 oxygens are going to go on the outside. Yes. Connect everybody up. 1, 2, 3, 4, 5, 6. We are now at 20, right? 1, 2, 3, 4, 5, 6. We are at 14. 1, 2, 3, 4, 5, 6. We are at 8. And you do not have to change this every single time. In fact, I do not even need to see this. If you can, I would strongly suggest at least writing how many electrons you were putting in your structure. But if you can just blast out a bunch of them and take care of that whenever you feel like you need to, that is totally up to you. Finally, 1, 2, 3, 4, 5, 6, which brings me to 2, which is a good thing because that phosphorus is only at 6 right now. So he needs 2 more. Okay. No weird resonance structure or anything like that because I ran out of my electrons. No need to make multiple bonds here, but I do need to, since he is a polyatomic ion, put him in brackets and the -3 in parentheses. Well, here's the cool thing. As we know, a positive cation of sodium can totally make an ionic compound with phosphite, which means after the crisscross, that -3 charge and the +1 charge, that just means I need 3 positively 1 charged sodiums to cancel out that 1 negatively 3 charged phosphate. So that's the ratio of each one of these ions I need to each other. So if I were to draw this dot structure, it would be the dot structure of that ionic compound made between the sodiums and the phosphites. But we need 3 of those guys to cancel off 1 of those guys. So technically, my dot structure for sodium phosphite would show 3 of those. And then you're all like, oh my gosh, this is so annoying. And there's lots of dots for us. And that's okay because we feel confident about our dots. And I'm drawing this structure kind of willy-nilly without following my rules because I'm literally copying off of the structures that we just drew with our rules. So I feel confident about that with a -3 charge. So this is an ionic dot structure between a normal metal cation and one of my polyatomic ions that we now know is all covalently connected together. And now that we know how to draw a Lewis dot structure, we see it right there, which is very exciting. Okay, so have fun with this. I'm excited.